This next example of the well-ordering principle, we're going to do a couple of somewhat straightforward examples, and then a non-straightforward example, which which explains a little bit why one of the hypotheses are necessary. So we're looking for the least element of the following four sets. So in each set, we want to find the least element. For positive even integers, well, that should be a 2. For positive odd integers, that should be a 1. And in C, we have positive multiples of 2024. Well, that should be 2024 is the first multiple of 2024. And there should be nothing less than that, which is a positive integer in our set. So a natural number in our set. Okay, and so that was somewhat straightforward. For our last one, let me remind you that the natural numbers start at 1, and when we want to include 0, we'll write it as n0. So remember, n0 is n union on 0. So in this set, we're looking for the natural numbers such that n is cosine of m. Well, we know that if we're going to look for a least element, we should maybe even just check that the set is non-empty. In the first three examples, the set was clearly non-empty, but here it's not so clear. So what do we know about cosine? Well, cosine's always stuck between -1 and 1. Right? So the only time that cosine of m could be equal to n, a natural number, is when cosine of m is equal to 1. So this condition, n is cosine of m, forces n to be 1. And so we need to solve cosine of m is 1. When is that true? Because that's the only time that we could ever have this equality. Scroll down a little bit there. Well, cosine of m is 1. This tells us that m is a multiple of 2 pi. However, the only time that a natural number is a multiple of 2 pi is when that multiple is 0. And the reason is because if k is not 0, k needs to be positive because our m's are positive. Then we get pi, by solving for pi, is m over 2k. And this tells us that pi is rational, which is a contradiction because pi is an irrational number. In fact, furthermore, pi is what's called a transcendental number, which makes it sort of even more irrational than irrational numbers, although that sentence doesn't exactly make sense. So this tells us that there's no way to write m as 2 pi k, where k is positive, because then pi would be irrational, and of course, maybe I should do my lightning bolt in blue instead to indicate contradiction. So what this is telling us then is if we go back, we said, well, the only way we can have a natural number in this set is if that natural number is 1, because cosine is always between -1 and 1. But the natural number 1 doesn't work. We can never find an m that makes that true. So actually, if we go back up here, we've just concluded that this set is empty. So this set has no elements. In particular, does not have a least element because it has no elements. So let's just be even real clear on the left here. No least element for D exists because the set is empty. And this just indicates the importance of actually checking that your set has elements, because otherwise, if you're playing with an empty set, sort of everything is true and nothing is.